So good morning all of you student. So last lecture we was to see here Bohr and Sommerfeld theory for hydrogen like atom, and we have considered the orbits here. So in general condition, one is the circular orbit and other is the condition is given by n-1. So this n-1 is the elliptical orbit, okay, and we have to see that if take n is equal to 1, then gives value for the r is the 0, and if consider as n is equal to 2, then r value is given by 0 and 1, and if you have consider n is equal to 3, principal quantum number. So taken the orbital quantum number, that L or R is equal to 0, 1, 2, okay, and with respect to shape of the orbital is which is orbit is the circular and which orbit is the elliptical. So consider the shape is here. So again we have to see that if n is equal to, consider for n is equal to 4 is here. So if n is equal to 4 is here, so k value is equal to 1, 2, 3 and 4. So if take n is equal to 4, k is equal to 4, then r is equal to 0. So this is the condition for the circular orbit, okay. If n is equal to 4, k is equal to 3, then r is equal to 1, n is equal to 4, k is equal to 2, then r is equal to 2, and if take n is equal to 4, k is equal to 1 and r is equal to 3. So these three orbit is the elliptical orbit, okay. So see here the shape of the orbit is for this n is equal to 4, k is equal to 4 and r is equal to 0. So this is considered as is the circular orbit shape, correct. And if n is equal to 4, k is equal to 3, r is equal to 1, then your orbit is given as the elliptical shape. So consider, so this is the flattened part of this, and we have know that the condition of the circular shape is the semi-major axis is equal to semi-minor axis, and condition for elliptical orbit is n by r, so that is semi-major axis divided by semi-minor axis. If so, this is for the k is equal to 4 and r is equal to 0. This orbit is given by k is equal to 3 and r is equal to 1. Now next is if k is equal to 2, then r is equal to also 2. So the shape of this orbit will be considered as the elliptical shape, okay, and this is for k is equal to 2 and r is equal to 2, and condition for the next for n is equal to 4, k is equal to 4. So for this is the condition for the k is equal to 1 and r is equal to 3 and n is equal to 4. So this is the semi-major axis and this is corresponding to the semi-minor axis, okay. So for give the example For these are the quantized orbit determined by 2 out of 3 quantum number. That quantum number is principal quantum number n, azimuthal quantum number k, and r is the radial quantum number, and given by equation. So this is with respect to equation that n is equal to r plus k. So for helping of this equation we have to find out the shape of the orbit, and normally the total principal quantum number n and azimuthal quantum number of theta are used to specify the quantum state. Okay, if you have the general example of, for example, n is equal to 4, so there are 4 different state, correct, and 4 possible orbit. Okay, if n is equal to 4, then how many orbit? So total 4 orbits, and all these orbit have same energy value. All these orbit have same energy value as determined by the same quantum number. Okay, if you have considered the state consider the same energy value, that is called as the degenerate level or degeneracy. Okay, so if the atomic state can be described by more than one set of quantum number which is correspond to the same energy are called the degenerate level. Okay, so for example, what, suppose if we have consider the degeneracy is taken by, so n1, n2 and n3. Suppose 2 1 1 1 2 1 or 1 1 2. Okay, if we calculate the energy here, so 4 square is 2 square is 4 plus 1 plus 1, so this is how much? 6. This is 6 and this is also 6 times of V E E. So for this different 3 energy state have the same eigenvalue of the energy called the degeneracy, and corresponding state is known as the degenerate state. And if the special theory of relativity applied to the motion of an electron, so if case of single electron system, that degeneracy is removed. Degeneracy is removed, and that an electron in elliptical orbit is not constant. It is more when electron is near to the nucleus. Okay, so here we have considered the point of the speed or velocity of the electron. Okay, so if we have considered in the orbital shape, so if is, suppose here consider the orbital shape. Okay, and suppose this is the semi major axis, this is semi minor axis, and suppose your nucleus have positive charge is here, one of the foci position is there. Okay, and suppose your electron position is here. Okay, so what is the velocity of electron is maximum if this electron is near to this nucleus. Okay, if electron position is nearer to nucleus, then the velocity of electron is maximum. If your electron is in the orbit is far away from the this positive charge nucleus, so then your electron velocity is the minimum, and that are late or less. Okay, so if mass of an electron is varies with the velocity according to the Sommerfeld, and path of an electron is preceding the ellipse. Okay, and the rate of precession is different for the different orbit. So if we want to the spectrum of the fine spectrum of the hydrogen atom according to the Sommerfeld model, so whatever, suppose if we consider, so ground state, inner ground state, energy state. So consider here, suppose for n is equal to 1, so we have here that orbital angular momentum, so that L gives the value 0, because main condition is L is give as the 0 to n minus 1, and if n is equal to 1, so that 1 minus 1 is gives the 0, then L is equal to 0. If we consider, suppose for example, n is equal to 2, then if n is equal to then 2, then L value gives to 0 to n minus 1, so that is how much? 2 minus 1. So 2 minus 1 is how much? 1. So L value gives here 0 comma 1. Suppose consider there have two energy state is there for L is equal to 0 and L is equal to 1. So for L is equal to 0 and L is equal to 1 is here. So if we consider this for n is equal to 3 here, so given value 0 to n minus 1, so that is 3 minus is 1, that is 2. So L value is given as 0 comma 1 comma 2. So for n is equal to 2, so give 3 different L values. So this is L is equal to 0, L is equal to 1 and L is equal to 2. So L is equal to 0, L is equal to 1 and L is equal to 2 is here. Suppose we have considered the spectral part is here, fine structure of the hydrogen atom. So for L is equal to 0 to 1, so allow transition from L is equal to 0 to 0, 0, 1 to 0, 2 to 0, so that electron jump from higher orbit to the lower orbit, so that will be considered here. So that 0 to 0, L is equal to 1 to 0 or 2 to 0. Okay, so this is transition from n is equal to 3 to 2, and for third orbit to the second orbit, so with corresponding energy state. And if we consider for L is equal to 1, so that transition from electron for principal orbit n is equal to 2 to n is equal to n is equal to 3 to n is equal to 2, so that have consider for 0 to 1, 1 to 1 and 2 to 1. Okay, so this is the fine structure of an hydrogen atom corresponding with the angular momentum, and these different orbit for the same n values, this gives the n different state of the side difference. With this, energy may be removed and degeneracy leads to the fine structure of an atom. So thanking of you, will be next lecture we have to see in the space quantization of an atom. Okay.